Hi, good morning. Today's lecture is data association techniques. Data association is about regarding the tracking that we have already studied in previous lectures. So, data association techniques is uh, most famous technique uh, in the tracking theory. So, what is definition? Data association is a process of associating uncertain measurements to known tracks. So here measurements is regarding the output of sensor like radar. So radar, whatever it receives the measurements from the surveillance region, these measurements are called uncertain measurements. So these measurements may be regarded with target and regarded with true target, regarded with false target, and collector measurement, everything. So radar receive plenty of measurements, and those measurements are uncertain. So data association is actually a you can say decision making procedure uh, which match the measurements match the measurement and select the some validated measurements and assign those measurements to known tracks, and then tracks are initialized with those validated measurements. Then it calculates data association probabilities for the object measurements. So here problem types that uh, track creation, maintenance, track maintenance, and deletion. So here track creation means track initialization. Okay, so tracks are initialized using two point measurements. Maintenance means that the track are automatically maintained based on the track existence probability. Means each track are initialized with initial probability of target existence, and at each scan the initialized probability of target existence are updated using the Markov chain theory, Markov chain model. So it update in each scan. We update target existence probability because in order to uh, maintain the tracks. So, for example, if the initial probability is initialized with 0.01, okay, so when we apply that association technique and when we update the target existence probability, it could be increased. It could be increased based on the detection of the target, based on the detection of the target, based on the detection of the measurements, and based on the measurements are detected and are originated from the target. So if we update the target existence probability, it may be raised to 0.95 or 0.97. So initially it was initialized with 0.01, but when we update using the data association, then it can be updated and increase the probability of the measurement increases from zero point zero 0.01 to 0.95 or 0.85. So so here in this way we can update the probability of target existence in each scan to maintain the track. So for example, if uh, some of the track having the target existence probability less than very less than 0.01, then the tracks will be deleted. So here deletion has threshold, and for maintenance have different threshold. Means to maintain the track, the probability should be 0.95 or 0.975, and for the deletion it can be 0.01 or zero point zero 0.02 or less than zero point zero 0.01. So we can read the track. So if the existence probability 0.01, it means there is no target. and the track or the tracking the collector or some random object, so we can delete the track. So other problem types is single and multiple sensor. There could be multiple sensor. We can install the multiple sensor and problem target detection. So target detection is another problem because the target detection is very low in the surveillance region, because in the surveillance region there are many objects. For example, in a single uh, room, in single classroom, there are many people, and other than people there are many other things like furniture, like uh, different noises, like the reflection of the body and the reflections of the uh, other random sources. So under those object, because these object generate the measurements, and the radar could receive the measurement from all objects. So whatever a true target, like a human may be a true target, or a vehicle is a true target, but this target is very less detection probability. So it is very difficult to estimate the position of the target, because it has very low detection probability. So each track is initialized with the initial target existence probability to identify its target, and then it automatically maintain and delete the target. And then the other type of problem we have, we will be facing that false alarm model and rights. There are false alarm model that is in the target model, and other than this, there may be a single or multiple targets. For a single target, the problem uh, is usually normal, but when multiple targets are entering into a service region, it will be more difficult, because because it will be difficult to assign the multiple target measurements to tracks. So track do not know which measurement belongs to which track, and tracks do not know which measurements belong to which target. So all measurements are uncertain. So if multiple targets entering service region, then it will be very complex situation and complex calculation uh, for uh, for knowing the actual measurement, and also the identifying the target, and it is also difficult to know which measurement belongs to which track and which measurement belongs to which target. So to solve these problems, we have different approaches, and the approaches may be Bayesian approaches like Kalman filter. Kalman filter, the Bayesian, which compute a full or approximation, approximate distribution in data association space from pairs, posterior belief, and observation. So as we study the mice formula is actually must have a, periodic PDF, periodic probability density function, and then it to calculate the posterior PDF. Okay. And then there is a non-Bayesian. In case of non-Bayesian, we compute the maximum likelihood estimate, like for example, the maximum likelihood estimation from the possible set of data association solution. So let's consider a different tracking paradigm. Object detects data objects in each frame, figure out the interframe correspondence between them. So also in each frame, we need to detect the object, and the object changes its position in each frame, and also in each frame the behavior of the object is also unknown. So we do not know the in the next frame what will be the behavior of the object, and also we have to figure out the interframe correspondence between them. So this is a rather natural way of looking at tracking if you are tracking blips on a radar screen. So for example, in the radar screen there is a um, the um, the light effect which reflects the blips on the screen. So it is very similar to this example, the tracking blips on radar screen. However, this approach, the data association approach, also prevails in the domain of automated surveillance systems. So this is, as I already told you, that data association is based on matching. It best match. It choose the best match between the two frame or two scan. So, for example, the two frame matching corresponding problems. So, in each frame, the data association match the similar thing. Like this is matched with this one. This is matched with this one. So, in this figure, it matches every corner of the image with each other. So, for example, the corners and the shift keys and the image batches. So like this one, like this one, this is the example. So this association is a decision making procedure which choose the best match and select the only best measurement for associating the best measurement to the tracks. And also it calculates the association probability. So based on association probability, the tracks uh, uh, update the state estimation. So state estimation are updated using the common filter, but before common filter we used data association to choose the best measurement. And this is another example in, between the two frame. Like this here is car, here's the car, same car, the same. For example, the features, color, size, weight are same in here, and there are other cars as well. But if we can if we are trying to track this car, so this car should be the same in both frame. So data association match the two frame correspondence, and here the another people is another people, so it match like this one. So this car and the two people going around. So match up detected blocks across the frame. So filtering framework, we want to recursively estimate the current state at every time that measurement is received. So like you have already done the common filter estimation algorithm, where you have to recursively estimate the current state at every scan based on the measurement received in that scan. So you have to update the state estimate based on the current scan measurements. There are two approaches, two-step approach. This is the filter. This filtering is a two-step approach. One is prediction and update. Prediction: propagate state PDF forward in time, taking process noise into account, translate, deform, and spread the PDF. Another update: use Bayes theorem or common filter to modify the prediction PDF. PDF means probability density function based on the current measurement. So here, which measurements should we update with? Okay, so the current measurement it should be ZK, means ZK is the current measurement. So here the observation is included with uh, true target and as well as false target and as well as the collector as well as all other random measurements. So we have to update the prediction using the current measurement. So as we know, there are plenty of measurements, so we need to add the getting. So getting and the filtering, there are the step prediction, propagate the state PDF forward in time, taking process noise into account, and getting to determine possible matching observations. So getting means it will create a window over a measurement. So those measurements which match to the observation are selected for the window. So we get the selected measurement instead of instead of associating all measurement that are receiving from the radar. We just make a small window across the best possible match of the observations. So data association to determine best match. So first getting is create a window uh, across uh, across a subset of the set of measurement, and then data association to determine best match, and then update, for example command filter to modify the prediction PDF based on the current measurement. So the overall procedure is make observation. uh, Measurement can be raw data, that is processed radar signal or the output of some target detector, and then predict the measurements from the predicted tracks. So this yields an area in sensor space where to expect an observation. So this area is called the validation gate and is used to narrow the search, because in the search space there are plenty of measurements, and then we should create a validation gate. Okay, so this this getting is like the validation gate. So we choose the selected measurements. So those selected measurements are called the validation measurements, and check if a measurement lies in the gate or not. If yes, then it is a valid candidate for pairing and match. After this step, the data association applied. So data association will select and associate validated measurement to the tracks. Okay, so for example, um, these are measurements Z1, Z2, and Z3, and in the service region only Z1 three measurement are validated. Only three measurement all validated, and in this way, using the validation gate, we ignore all other measurements, because those measurements are not matched with our interest with our interest, and this is predicted measurement, or you can say the initialized measurement, initialized track prediction. Like as we already know, that track are initialized using two-point measurement. So when you apply two-point initialization procedure, then it calculates the measurement prediction. Okay, like uh, like the updated PDF, like this one, like this one. Okay, like this one. So this is the predicted measurement that track have, and these are validated measurement. So the first step is make observation, the raw data, and from the raw data predict the measurement from the predicted trace, that is Z1 and the upper cap, and develop a validation gate, and which is used to narrow the search, because in the search area there are other plenty measurements, and check if measurement lies in the gate or not, and check if this predicted measurement Z1 is lies in the gate or not. Yes, here it is. Here it lies in the validation gate. If yes, then it is a valid candidate for pairing and match. So this is a valid candidate for pairing and match. This is called the best match. Okay. Now, what makes this a difficult problem? First one is a multiple target, because it make multiple association, and we do not know the which measurement belongs to which target. And also in the same way, sometimes the two tracks sharing the same measurement. So multiple targets is very difficult, because it is difficult for the data association to decide if the two tracks sharing the same target. Although we do not want to let two tracks to select the same target. We want in multiple target scenario, we want that each track have their own target. But uh, it always happen that the two tracks having the same measurement. So there's a problem. So, and also false alarms, false positive detection, and detection uncertainty. So detection uncertainty in the occlusion region, due to the occlusion region and sensor failures. Sometimes due to the occlusion and sensor failures, target may disappear. We cannot see it, though target lie, but the sensor cannot observe the detection, because the occlusion region and the sensor failures. And other thing, ambig ambiguities. There are several measurements in the gates. So due to several measurements, the gate the detection are uncertain. And here these formulas are, you already know these formulas, and before apply the getting process, you should know the measurement and the measurement covariance prediction, like this formula. And this is the sensor measurement noise, sensor measurement noise. And if only position of the target is observed, then we use this one. Like this, if we multiply this thing, then this is the two dimensional position. And here h is this one. And also one can also observe velocity and acceleration using the accelerometer, and the velocity using the Doppler radar. Then validation gate, assume that measurements are distributed according to a Gaussian centered at the measurement prediction zk with covariance sk. Then this is called the measurement likelihood model. So measurement likelihood model, um, calculate the likelihood of the measurement prediction, which have covariance like this one. Okay, so it calculates the likelihood of the measurement prediction based on the current skin measurement. So okay, and for the generation of the validation gate, we use the Mahalanobis distance between the x and the nu. So this is the Mahalanobis distance between x and nu, and x is the observation, and nu is the mean value of the observation. And this is a formula for calculating the distance between the observation and the mean value of the observation. And c is a constant. And then the measurements will be in the area, like how to calculate the area. Like if the validation get shape of the validation get is ellipsoid, then what will be the area? So here is the formula for the area. So this area may be equals to this thing or this thing. Means we can calculate the area using this thing, and if the distance is less than gamma is a chi-square distribution threshold, and other way is to use this thing where z is the observation and z cap is the mean value of the observation, having the covariance, and means we can first calculate the difference between the observation and the mean value of the observation, having the transpose, and this is without transpose, and if this is less than the gamma, for example gamma is 0.95, okay, and we calculate the distance between this thing. So if it's less than, then those measurements are selected, suppose this is a validated measurement, so the output of this equation is called the z, and this sign. So the output of this equation is the validated measurements. So validated measurement are selected using this threshold. So with the probability defined by the gate threshold gamma. So here we omit the indices. So this area is called the validation gate. So there are two ways to calculate the validation gate and the area of the validation gate. The threshold is obtained from the inverse chi-square cumulative distributed at a significance level alpha. So this is a chi-square distribution, cumulative distribution. Now the shape of the validation gate is a hyper ellipsoid and two-dimensional. This follows from the setting this equation, which gives you uh, this, which gives you value of c. The gate is defined by isoprobability contour obtained when intersecting a Gaussian with a hyper ellipsoid plane. So what is this? This is actually the formula for uh, the you can say uh, like this one, like this one, for selecting the measurement. So for creating the shape of ellipsoid gate, we apply exponent here. We apply exponent and multiply exponent of this power with this factor 1 upon 2 pi k over 2, and the covariance square root of covariance. So this will create a ellipsoid gate, and if this threshold is less than some threshold like gamma, then those measurements will be selected for the validation gate. Why chi-square distribution? Let xi a set of k uh, IID distribution, standard normally is distributed random variables. So for example, xi is normalized with the mean 0, and covariance unity covariance. Then variable q is equals to the sum of x values. So this is the chi-square. This follows the chi-square distribution with the k degree of freedom. So we will now show that Mahalanobis distance is the sum of the squared standard normally distributed random variables. Assume 1D. Assume 1D measurement. Where, for example, the mean value is the zk is the mean value, and sigma is called it's a standard deviation which is equal to the covariance. Then distance is then this thing. Okay, this is the same thing. but we want to show that this is a chi-square distribution, and suppose if we multiply and to solve try to solve this thing, then this will equals to this one. By changing the variable y equals to z minus nu over sigma, we have this one. So here we can say that y is normalized with a zero mean and unity covariance. So d equals to y square. So does d equals to y square here, and is a chi distributed with 1 degree of freedom. Assume n dimensional measurement, and here we suppose mean value is z k, and the sum of because we are considering n dimensional, so sum of standard deviation equal to s k, and this distance the same in the same way distance equals to here, but here we replace the sum because for the n dimensional measurement, here is a the same thing. By changing the variable y equals to c minus 1, where c is the Korosky decomposition is a constant value, and c inverse z minus nu. Let we let change the variable y equals to c inverse z minus nu, and summation equals to c into c transpose. We have y normalized with zero mean and identity matrix, because the previously only one dimensional, so we write only one. And if we have n dimensional, then we can write identity matrix with dimension of the observation, and therefore the d equals to y transpose y inverse and y. So here y is same as this one, and I inverse, and where I inverse is the covariance matrix, and y, and then again is equals to the this thing. This, so again we can say this is the y is the chi-square distributed with a k degree of freedom. Why does the where does the threshold come from? So the gamma, often denoted by chi-square, is a chi-square k scan gamma alpha. So actually the chi-square is a cumulative distribution. Gamma is taken from the inverse chi-square cumulative distribution at level of alpha and k degree of freedoms. The values are typically given in the table. For example, in most statistical book or by metal function chi-square inverse. And given the level alpha, we can now understand the interpretation of the validation gate. Suppose the validation gate is a region of acceptance, such that 100 into this percentage of 1 minus alpha of true measurement are rejected. So the typical values of alpha is 0.95. So what is alpha? Alpha is actually the uh, probability of the chi-square distribution. So we always choose alpha here. We always choose alpha here 0.95. 0.95 here. 0.95. So the distance between 0.95, those measurements where distance is less than 0.95 are selected for the association. For example, there are some measurements, and we calculate the distance between IB and distance between IA, IB, JA, JB. So here the triangle sign is observation and plus sign is a prediction. So we want to calculate we want to match the prediction with the observation. Observation is a sensor observation. This is sensor observation, and we want to develop the validation get by matching the prediction and the observation. So it takes into account the position, uncertain, uncertainty, and correlation. So it seems that IA and JB belong together. IA is a distance of 2.24 and JB is 1.5 n. So it seems that it is close to this one. This is close to this one. So it seems that the distance between the IA and the distance between the JB are close to each other. So we can match this thing. For example, IA, I and A, IA, and here IB, IB. So observation and IB. So the distance with a diagonal covariance matrix takes into account position and uncertainty. So other value could be uncertain. Okay, if if one value best match or one value is closely if two if a prediction is close to the observation, that then it is a position, and other value could be uncertain. We do not know because this that value is lie far. So now IB is closer and then JB. Okay, now IB, so distance between the IB is 3.14 and then JB 3.41. So it seems that 3.14 IB is closer. So IB, where is IB? This is I and B is closer. And the distance between the JB is maybe uncertain measurement. This may be uncertain measurement. So here distance is closer. IB is and this. So next, we can see that IB and JA that belongs together. For example, IB is 2.77 and JA is 2.44. So I think the distance between IB and JA belongs together. So here I IB belongs together, so it makes the same validation gate, and then uh, JA, this is JA, makes the same validation gate. So the validation gate to combine, yeah, combine, because the distance distance between the I and A are very close together, so they belong, and also the B and A combined, I and B combined. So here the scenario. Now let's see another scenario for the data association. For the multi-frame matching observation in a new frame to a set of tracked trajectories. Suppose a square shape measurement is track 2 and the rectangular shape is track 1. So, and here these are the observation in the current scan. These are the current scan observation, and suppose in current scan there are two tracks. So still the data association do not know, and how to determine which observation to add to which track. Means we should add this measurement to this track or this measurement to this track, because each track should have only one measurement. and but here three measurement, here two measurements. So uh, here which measurement to add to which track. Okay, so that's why we use the validation get, and we match the best possible matching. So for example, this measurement is matched to this track, and this measurement is matched to this track number one. So we should to predict the next position along each track. So here we predict the measurement along each track. Next, match should be close to predicted position. So here we should to determine the data association should decide the match should be close to the predicted position. If this is a predicted position, then we should calculate the distance between other observation, between the D3 and between the other observation. Like there are uh, 3, 4, 5 measurements. So we should we should calculate the distance, D1, D2, D3, D4 up to D5. We should calculate the distance. Now some matches are highly unlikely. So here some measurements are highly unlikely, and we cannot select those measurements which are unlikely, and we should select those measurements which are highly likely. So here the most likely match is this measurement. So we can assign this measurement to this track and this measurement to this track. So for example, here the procedure for getting a method for pruning the matches that are geometrically unlikely from the start allows us to decompose matching into smaller subproblems. So suppose this is the proper matching here. This is proper matching in the validation gate, and also it should be noted that each track develop their own validation gate. So this track has its own validation gate, and this track has its own validation gate. So in this validation gate, this is selected, and in this validation gate, this is matched. And then once it's matched, we can apply the Bayes theorem by Kolmogorov filter, and we can apply the prediction and update. Like this is you already know. And here Kolmogorov filter, for example, this is the best match. Then uh, we can propagate using the this is suppose xp equals to f into x minus 1. Suppose if x k plus 1 equals to list 1, we can up we can update k plus 1 by multiplying the transition matrix to the state previous measurement, and then this one, and this is the uh, getting threshold. For example, why this is innovation, same thing. This is the same thing, like z minus z mean is inverse transpose transpose z minus z mean is in gamma. So this is validation area or threshold, and this is the gamma filter. By selecting this measurement in the validation gate, we apply the gamma filter propagation, and then when then we apply the update equation. This is a prediction step. Now what happens in the validation gate, there are other measurements. So this is the other method, a global nearest neighbor. So we should calculate the Mahalanobis distance between the neighbored neighbored measurement like O1, O2, observation 1, observation 2, 3, 4. So this is the distance. These are the distance point 3, 5, 6, 9, and so A I J. This is A I J. The score of matching observation J to track one. So J is a level of track level of track the track level, and uh, it defined the could be based on Euclidean or Mahalan based distance to predict the location, and exponent d square could be based on similarity of appearance and appearance temple correlation score. Suppose the the maximum value 0.9, so it choose the maximum value of the distance, choose the best match by maximum value of a11, a22, a31, and a41 for the track one. So this is the track one, and suppose two tracks. If there are two tracks, then we should calculate the AI for the track one. This is the track one, and this is track two. So here the maximum value for the track one is zero point 0.9, and here the maximum value for the track one is zero point 0.8. But this belongs to the same observation. This is observation one. This is observation one. Is O1, O2, O3, O4, O5. So O for track one has a observation 4 with a maximum value of 9 with maximum score of 9, and here track 2 has a maximum score for the observation 4. So here we can see that both both tracks try to claim observation of 4. So these are some difficulties in data association, and next in the next class we will see other problems like the false alarm and detection, um, target detection, and these things. Uh, we will study target detection and false alarm and rates and single emitter targets, and then first we should understand the problems in the data association. Then we will try to apply the Kalman filter uh, for to solve the data association solution. Okay, see you, bye.